Welcome back to Physics 371 Online. We'll finish our discussion of the sources of magnetic fields in Chapter 5 by considering the multipole expansion of the vector potential A. And we'll be doing this mathematically in almost exactly the same way as we considered the multipole expansion of the electric potential back in Chapter 3. And it exploits a mathematical similarity between the two problems. So, the goal is to express the vector potential in a power series in 1 over r, where r is the distance between the current and the point P. So, in order for us to do this, we have to have a localized current, which is why I've drawn in this figure a current loop that closes on itself, carrying a current I. So the point P, where we would like to express the vector potential, is the distance r away from the origin, as shown in the figure. Then we break down the current itself into length elements, dl prime. Of course, those are located from the origin by a vector r prime. And then finally there's a third vector, script r, that goes from the current element to the point P. And this is a familiar geometry that we have used all the way back in Chapter 2 when we were dealing with electric fields. What I can't show very easily on this diagram is that the angle between r and r prime vectors, that angle is theta prime. So, from our solution to Ampere's law, we know as our starting point that the magnetic vector potential can be written mu naught I over 4 pi times the integral along a path of the vector dl prime over script r. And just as we found for this same geometry when we discussed electric potential, we can write down again this power series expansion of 1 over the distance script r, which appears in the integrand for the magnetic vector potential just like it did for the electric potential. And so this expansion can simply be substituted into the expression for the vector potential. And just as I said a minute ago, theta prime is the angle between vector r and vector r prime. And so this theta prime that appears in the argument of the Legendre polynomial is that vector. So, for the localized current, as I said, we have a closed current loop, and so that integral that is part of the expression for the vector potential is a closed loop. And so from now on, in the integral signs that we write, we'll write it as a closed loop, integrating this quantity dl prime over r around the loop. So by substituting in for 1 over script r, we see that we have an integral dl prime times all the terms in this power series expansion. And since the integral of the sum can also be written as the sum of the integrals, by doing a little bit of rearrangement, we pull the mu naught I over 4 pi out in front, and now we have a summation over n of the quantity 1 over r to the n plus 1, because we had a factor of 1 over r, and then we had a factor of r to the n here, times the integral around this closed current loop of r prime to the n times p sub n of cos theta prime times dl prime. And note here it's important that the dl prime is a vector. A is a vector quantity, and so we're integrating this length element dl prime, only it's not just a length, it is a vector quantity. Now let's write this expression out term by term because it's kind of revealing. We can see the different terms and identify them one at a time. So the mu naught I over 4 pi gives us, for the n equals 0 term, we have a 1 over r, and then the only thing that's left in the integrand is dl prime vector. So integrating around a closed loop, this differential vector dl prime takes us from the beginning of the loop all the way around to the end. And remember, this is a vector sum. Right? So we would take, if we numbered these individual terms, we would take dl1 plus dl2 plus dl3, and if we close back on ourselves and end up at the starting point, then the vector sum of all those individual vectors will be 0, because there won't be any net displacement as you go all the way around a closed loop. So this term, which is known as the monopole term, is exactly equal to 0 for a closed current loop. That means that the dipole term unless it happens to be 0, is going to be the dominant contribution to the vector potential. We see the quadrupole term and then the octupole term and so on as we go further out in the power series expansion. Now, the dipole term then can be written mu naught I over 4 pi r squared times this integral r prime cos theta prime dl vector prime. And we can actually do a little simplification of this and write it in a form that is pretty handy, because it separates out the contribution of the loop to the geometry of where the loop is located with respect to the point in question. So right away, this r prime cos theta prime can be written as r hat dot r prime, right? Because the r hat vector has length 1, the r prime vector has length r prime, and 1 times r prime times the cosine of the included angle gives us what we had in the argument to start with. So this r prime dot this r hat dot r prime vector simply expresses the integrand. And now here's something that I'm not going to show you, but simply appeal to an identity that is back from chapter 1 in the book that shows that this integral around a closed loop can be transformed into the cross product of our friend the r hat unit vector and a surface integral dA prime. So the loop that's in question here around which we're integrating also defines a surface. And so integrating around that surface this dA prime vector and then taking minus the cross product r prime cross that gives us exactly what we had in the original expression. And it's kind of handy then to get rid of the minus sign. We'll just change the order of the cross product so that we have now mu naught I over 4 pi r squared times the integral dA prime over the surface that the loop bounds cross r hat. Now, what we see here is that there are some of the terms in this that depend on the location of the point in question. For example, the r is the distance from the loop, or from the origin near the loop, to the point in question, and r hat is the direction of that point from the origin. And so those are just geometrical factors that happen to do with the location of the loop, or actually with the location of the point. However, the current and then this surface integral, those are properties of the loop itself. And so let's make a definition here, a quantity that just reflects properties of the loop. So it's this I times the integral dA prime, and we will call that m. Many textbooks use mu for this quantity, but since mu comes into play in the case of mu 0 and also in magnetic properties of materials that we will discover in chapter 6, Griffiths prefers to use m vector to define this quantity, and it's called the magnetic dipole moment. It's very analogous to P, the electric dipole moment, in the theory of the multipole expansion of the electric potential. So making that definition, we can take our expression for the dipole contribution to the vector potential and write it like this: mu naught over 4 pi times m cross r hat over r squared. And remember, there's no I here because that got incorporated into the definition of m. So in many cases, we deal with a planar current loop. And so that would make the evaluation of that area vector very simple. The magnetic dipole moment would simply then be the current times the vector area of the loop, where, of course, by convention, the direction of that area vector is perpendicular to the plane of the loop. Now, it's also useful, and we'll just end our discussion today talking about this, to calculate the magnetic field produced by an ideal dipole M. All right, so here we have the vector potential, and all we really need to do is take the curl of that, and we'll get the magnetic field due to a dipole. And we assume now we have an ideal dipole, so that if it's a current loop that defines the dipole, it's a very small current loop, so that the size is essentially negligible. And we represent this in our diagram by a little arrow that represents the magnetic dipole moment. And you probably will notice that you've seen a picture much like this before when we were talking about the electric dipole and the potential and the field that it produces. So what we're going to do is take a point in space, which is at coordinates in spherical coordinates r, theta, and phi, and at that point we will calculate the magnetic field from a dipole. So first of all, we can take m cross r hat. Right here is the m vector along the z-axis. R hat is along the radial direction, and the cross product of those two is the magnitude of m times the magnitude of r hat, that's just 1, times the sine of the angle, right? But then it's in the vector direction given by the right-hand rule that would be the direction of increase of phi, or phi hat. So again, right-hand rule should confirm for you that m cross r hat is in the direction phi hat. So I replace m cross r hat with m sine theta phi hat. And having done that, now I see that this vector for the dipole contribution to A has only a phi component, but that phi component has both theta and r dependence. So you'll take the curl in spherical coordinates, and it's a calculation that's not that difficult. Everybody should really work it out. Just take out a pencil and paper and look at the definition of the curl in spherical coordinates from your textbook, and then use this expression for the vector potential of a dipole and do the calculation. And what's really, really amazing is that it turns out there's a very deep physical similarity between the magnetic field of a magnetic dipole and the electric field of an electric dipole, because this result here, apart from having a p in place of m and having an 1 over epsilon 0 in place of mu 0, the two expressions are identical to each other. It has exactly the same form as the electric field of an electric dipole. And these formulas are very useful when we start to deal with the influences that magnetic dipole moments have on other particles in their vicinity. So we'll work out some examples in class, and that is where I will see you.